Alright, so hopefully you've had a chance to look through the exercise. You'll get a lot more out of what we go over here in the video and on the slides if you've had a chance to think through it first before I give you the answer. Again, if you don't, you'll sort of have this, okay, well, I could have figured that out if I had taken the time to do so, but you won't have given yourself that practice to sort of prove it to yourself and to sort of build those synapses in your brain through practice. Alright, well, the first question in your exercise is, how many subproblems are there at a given level L? And as a reminder, the top level is 0, the second level is 1, and the bottom level was log base 2 of n. So the easiest way to do this is just to build a table and say, okay, if I'm at level L, how many subproblems were there? So number of subproblems. Well, at level 0, I have just one blob there, so 1. At level 1, I have 2. At level 3, I have 1, 2, 3, 4. And all the way down at the bottom, at level, log base 2 of n, I have n. So the task for this exercise was to sort of build a table like this. You didn't have to do it exactly this way, but it was to try to come up with an equation that matches this. So an equation where you plug in 0 and it gives you 1. You plug in 1 and it gives you 2. You plug in 3 and it gives you 4. So the only equation that does that is 2 to the L, which makes some intuitive sense. So at each level you're doubling, so which means you're going to multiply by another factor of 2. So here we've got 2 to the 0 is equal to 1. Here we have 2 to the 1 is equal to 2. At this level we have 2 squared is equal to 4. So 2 to the L is the number of subproblems at a given level L. So we needed some function that was based on L. Alright, so your next question here is, how many elements are there for a given subproblem found in a given level L? So for example, we're going to build another table. Here we had all n elements. Here we have 4 elements. Here we have 2 elements for all those subproblems. So we can build another table and we can say, given L, what's our number of elements? So at level 0, we're going to have all n elements. Or if you wanted to look at this exact version, you could say 8. I have all 8 elements. At level 1, I have n over 2. Or, I've got 4 in each of them. Level 2, I'm going to have n over 2 over 2. Or I'm going to have 2 elements. All the way down to log base 2 of n, I'm going to have 1 element. So what's a function that gives us that? It's going to be n over 2 to the L. So the intuition behind n over 2 to the L is that, if you notice, at every single level, I have all n elements. So here I've got 8 elements, here I've got 8, 8, 8. So I'm going to have all n elements at each level. I'm just going to evenly divide them among the 2 to the L subproblems. So you could just take that and plug it in there. I'm going to evenly divide my n elements among the 2 to the L subproblems. Alright, let me get my face out of the way. The next question is, how many computations are performed at a given level L? So the total cost of merge was 21m. That's your hint. So if I look at the total cost of the total number of computations at a given level, I'm going to need to know, well, how many times, or how many subproblems are there, So 2 to the L is the number of subproblems, and I'm going to need to know, well, what does each subproblem do? Each subproblem is going to do 21m amount of work. Alright, well, what is m? Well, for each of those subproblems, m is going to be, well, how many elements do I have for each subproblem? So I'll have 2 to the L times 21 times n over 2 to the L. Well, if you notice, I can cancel out my 2 to the L's, and I'm going to have 21n at each level. So I'm doing 21n work here, 21n work here, 21n, 21n. So I'm having 21n amount of work at every level. So what's the total computational cost of a merge sort? It's this 21n times the number of levels. So 21n times the number of levels, which we said is log base 2 of n plus 1. The plus 1 is because we have this as the bottom level, and this because we have a level 0. So before we start dividing by 2. So if you want to look at this a little bit more abstract, we have n divided by 2, divided by 2 again, divided by 2, all the way down until you get to divided by 1. Alright, so let's summarize merge sort. It's a divide and conquer style algorithm. It's constantly halving the problem size, then merging them together. So we start out with n elements, we divide it in 2, and then we merge those back together, and it does that recursively. The total running time is going to be roughly 21 n log base 2 of n plus 21. And you can compare that to the average running time of insertion sort, which I'll just kind of throw out a half n squared here. I'm going to put half n squared because you know the best case was big O of n, and the worst case was n squared. This is sort of an uneducated average running time, but just to give you an idea. So for small values of n, this half n squared is actually going to give us better performance. But for larger values, we'll get a better performance out of merge sort. So this one here. Alright, so which algorithm is better? Well, better kind of depends. So if I plug in, for example, 5... sorry, I've got my colors wrong here. This really should be the blue line, and this blue one should really be... This orange number here should be the blue line, and this blue number here should be the orange line. So if I look at a linear 5n, that's sort of the best case of insertion sort, and compare that to the average or worst or best, it's all the same for merge sort here. If you look for up to some number of elements, insertion sort is actually better. So that's what this plot is telling you, is insertion sort is better up to some number of elements. But pretty quickly after you get past that some number of elements, merge sort is going to be much better. Sorry. My problem here is this 5n should be in 5n squared in both places. Let me make that correction on my slides. The corrected slide should be uploaded, but in the video here, for annoying reasons, I'm going to have incorrect slides. Alright, so when you're talking about which one is better, it depends. Well, let's plug in a couple of... That's an n squared again. Let's plug in a couple of different numbers just for comparison's sake. What happens if I reduce that constant in front of insertion sort and increase the constant in front of merge sort? Well, because this is n log n and this one up here is n squared, so n squared there, n log n here, merge sort will still be better at some threshold. So it'll still be better on bigger inputs. So to quantify that some algorithm is better on bigger inputs, in the next set of slides we'll start looking at asymptotic complexity. So the first thing that should really jump into your head when I talk about asymptotic complexity is this idea of big O.